here's the third kind of important space that we're going to be looking at, and this is called the null space of a matrix. And this has to do actually with the homogeneous space of, with the homogeneous system associated to the matrix. So once we have a matrix, we can construct the homogeneous system AX equals 0. Its solutions form the null space. You may remember one of the exercises that I gave you in the past was to check that in fact the solutions of a homogeneous system do form a vector space. Well, that space is called the null space of the matrix A. All right. If you haven't done that exercise so far, well, you want to do it now. Okay. Now, how do we get a basis? Same idea. How do we get a basis for the null space from the matrix itself? Well, there is something peeking out of from there, so let's see what it is. What we're going to be doing is we're going to be looking at the solution set of the matrix itself. Okay, so what we're going to do is we're going to use either the REF of the matrix or the RREF in order to have a look at the solution set. Okay, again, this is best done through an example. So let's look at the same matrix that I showed you before. Now you can compute, you can use your calculator or by hand to figure out that the RREF, actually this is, well, yes, it is an REF, but it is also an RREF, it's in reduced row echelon form, is given by this particular matrix. From it, we can read the solutions of the homogeneous space. Remember, how do we do that? Each row can be read as an equation. So the first row reads x1 plus x3 minus 2/7 x4 equals 0. Remember, this is a homogeneous system. And the second row reads x2 plus x3 plus 4/7 x4 equals 0. Alright, so what we can do is we can write down the solutions of this system and say that, okay, what does the solution look like? The last two columns, which correspond to the last two variables, are in fact free, right? They correspond to free columns, and therefore they can take whatever values we want. And so let's say that those values are called S and T. And then x1 and x2 are going to be written in as functions of them. So x1, well, from the first equation we have that x1 plus x3 minus 2/7 x4 equals 0. Move that to move the x2 and x3 to the other side, write them as S and T, and do the same for the second variable, and this is what you're going to get. I suggest that you pause for a second and check that in fact you agree with me that that is the general solution of the system. Done? Okay, now I can write that expression as a linear combination of two fixed vectors by separating the s's and the t. So what I can do is I can write the s's separately and the t separately. So the s's get multiplied by -1, -1, 1, 0 in the 4 rows, and the t gets multiplied by 2/7, -4/7, 0, and 1 in the 4 rows again. So what that means is that the solutions of this homogeneous system are a vector space, and they consist of all the linear combinations of these two vectors. Well, that means that those two vectors are a basis, isn't it? And therefore that's how we find our basis for the null space. Notice that in this case we had to go a little bit further than the REF. We had to actually go all the way to the RREF. We can do it from the REF itself, but probably it's a good idea to go to the RREF because you'll have to go there anyway to get the solution, right? But at least we were already halfway there by computing the REF of the matrix. And here we come to this important theorem that I mentioned to you. Now, at this point, in this context, this theorem will not look very important, very big, but it is going to be quite more interesting later on. And in fact, it turns out to be a very interesting, important theorem for more advanced uses and more advanced developments of linear algebra that we're not going to see in this course, but I hope you will see in a later course. What does this dimension theorem say? Well, notice that the dimension of the null space, which by the way is called the nullity of the matrix, okay, is the number of what? It equals the number of free variables in any REF, certainly in the RREF, but in any REF, okay? On the other hand, we noticed earlier that the dimension of the row space or the column space is exactly equal to the rank, which is the number of pivotal variables, of basic variables, right? So now each column corresponds to either a pivotal variable or a free variable. And therefore, great big important theorem, if you add up the dimension of the row space and the dimension of the null space, what do you end up with? Well, you're adding how many pivotal columns you have plus how many free columns you have. What do you end up? The total number of columns. Okay, so this looks like a very important, very simple theorem in its statement, but turns out to be quite important. In fact, once again, we're going to be able to generalize this theorem to all vector spaces. Notice this is only true for the subspaces of that come from looking at the row space, the column space, and the null space of a matrix. Okay, so it's very much restricted to Euclidean vectors, but we can actually extend it. We'll have to do a little bit of construction and generalizations to do that, but it can be extended to all vector spaces. So all we're saying here is that the rank of a matrix, what is the rank again? Yeah, it's the dimension of the row space. So the rank of the matrix plus the nullity, what's the nullity again? Yes, the dimension of the null space. So I can read that same equation by saying the rank plus the nullity is equal to the number of columns. And that's the big dimension theorem.